Hi, good day to you everyone. My name is Alaika Medumaikas, and today I'd like to talk about a concept that is integral to many aspects of our lives, the groups. Whether we realize it or not, groups are all around us, influencing how we think, behave, and achieve our goals. Think about the different groups you're part of: your family, your circle of friends, your project team at school or at work, or even the sports team you cheer for. Each of these groups brings people together for a common purpose, providing support, sharing knowledge, and achieving what might be impossible alone. So, ladies and gentlemen, I think we're ready for the textbook definition of a group in abstract algebra. Are you ready? Alright, so a group is a set of elements. Notice I said elements instead of numbers. Element is more abstract. The group has one operation. Let's use an asterisk or a star to be more abstract. If you combine two elements in the group, the result is also in the group. A group is a closed under the operation. Each element has an inverse. If you combine an element with its inverse, you get an element we call identity element. It's common to use the letter E for the identity. Lastly is the associativity. Without associativity, you couldn't solve a simplest of equation. So ladies and gentlemen, that is a group. So, at the end of the lesson, the student should be able to define and understand the basic concepts of groups and properties. Determine the ordered pair of A and star constitute a group. Identify whether a given is a group or not. Prove basic results involving various types of groups and solve basic problems involving various types and its subgroups. Abstract algebra is a field of mathematics that studies algebraic structures such as groups, rings, and fields. It extends the familiar algebraic concepts from elementary algebra to more complex structures. One of the foundational elements of abstract algebra is the concept of a group. So, in understanding groups, it requires some preliminary knowledge of basic algebraic concepts. So, first is sets. A set is a collection of distinct objects considered as an object in its own right. For instance, the set of integers z, the set of real numbers r, and the set of complex numbers c are all fundamental examples. Number two is binary operations. A binary operation on a set is a rule for combining two elements of the set to produce another element of the set. Common examples include addition and multiplication. Number three is functions and mappings. A function is a relation that uniquely associates members of one set with members of another set. In the context of groups, homomorphism structure preserving maps between groups are particularly important. And now let's take a look at this. So let G be an empty set. A binary operation star on G is defined as A star B for all A and B is element of a group or G. Now, in a closed binary operation star on G is defined as a function of G star A and B is equal to A star B such that A star B is an element of a group. Then G with a closed binary operation star, G in star is a group if all the following conditions are satisfied. First condition is associativity. So if A star quantity B star C is equals to A star B star C for all A, B, C is element of G. Next condition is identity. There exists an identity if E element G such that E star A is equals to A star E is equals to A. Next condition is inverse. For each element A, element G, there exists an element B, also element G, such that A star B is equals to B star A is equals to E. In other groups, a group is a non-empty set associated with a binary operation that satisfies a certain actions. The operation must be closed, associative, and have an identity element. Additionally, every element must have an inverse. Now, let us take a look at this equation. So, x plus 3 equals to 5. So to find the x, the first thing we need to do is to add negative 3 both sides. And then we will perform the operation first on the right side. So that will gonna be x plus 3 plus negative 3 equals to 5 plus negative 3. So that will be x plus 3 plus negative 3 equals to 2. Next, if we add 3 plus negative 3, it will be equal to 0. So let's move the 0 into the right side, and that will be x equals to 2 minus 0, so x is equals to 2. So the properties are integers under addition, inverses closed under addition, associativity, and identity. Let G and star be a group. Then G star is called an abelian group. If A star B is equals to B star A, for all AB is element of G. That is the group that satisfies the commutative property. Now in semigroup. If the set G satisfies only closure law and associative law, then G is called a semi-closed group or semigroup. Now, infinite and infinite group. Any group G contains only a finite number of elements, then group G is called a finite group. Otherwise, group G is called an infinite group. Order of groups, the number of elements in a finite group G is called the order of a group and is denoted by the O quantity G. That means if the number of elements in G is n, then O quantity G minus n. Now let's move on into the terms. The first is set. So the notation for the set is G and the meaning is a set. Next is set with operations. So the notation is G and star and the meaning is a set with an operation. Next is semigroup. So the notation here is also G and star and the meaning is a set with an operation that is associative. Next is monoid. So the notation here is also G and star and that means a set with an operation that is associative and has an identity. Next term is group. So the notation here is also G and star and that means a set with an operation that is associative, has an identity, and has an inverse. Next is the abelian group. So the notation here is also G and star and that means a set with an operation that is associative, has an identity, has an inverse, and is a commutative.
Hello everyone, I am Christian Sanel and I'm going to discuss about the examples of the group. So here in example 1.1, the sets of Z, Q, R, and C with addition plus are groups with the identity of 0 in each element A and inverse of negative A. So Z stands for integers, Q for rational, R for real, and C for complex. We can consider this set is a group if all the following conditions are satisfied. First, if it is associative. Second, if it has identity. And third, if it has inverse. So let's verify these sets is a group. First, in associative, A plus the quantity of B plus C is equal to the quantity A plus B plus C for all A, B, C is an element of integers, rational, real, and complex. For the identity, there exists an identity of E is an element of integers, rational, real, and complex, such that E plus A is equal to A plus E is equal to A. For the inverse, for each element A is an element of integers, rational, real, and complex. There exists an element B is an element of integers, rational, real, and complex, such that A plus B is equals to B plus A is equals to A. So therefore, the sets of integers, rational, real, and complex with additions plus are grouped with the identity of 0 in each element A in an inverse negative A. This verifies that these sets are satisfied the group properties under additions. For example 1.2, the set of integers with multiplication is a monoid, has no inverse, and is thus not a group. Why? It is a set with an operation, is closed, is associative, and it has an identity, but does not have an inverse. The definition of monoid: a monoid is a set of M equipped with a binary operation that satisfies the following properties. First, if it has closure. Second, if it has associativity. And third, if it has identity element. So let's verify the sets of integers with multiplication. In the closure, the product of any two integers is an integer. If a, b is an element of integers, then a times b is an element of integers. In the associativity, multiplication of integers is associative. For any a, b, c is an element of integers, then the quantity of A times B times C is equal to A times the quantity of B times C. For the identity element, the number 1 is the multiplicative identity in integers. For any A is an element of integers, A times 1 is equals to 1 times A is equals to A. So therefore, Z for integers with multiplication satisfy the following properties. It is indeed a monoid. So let's verify the inverse of the sets of integers with multiplication. To determine the sets of integers with multiplication is a group, we need to check if every element A is an element of integers except 0, as an inverse in integers under multiplication. For the identity element 1, its inverse is itself since 1 times 1 is equals to 1. For A is equals to 2, to find an inverse B such that 2 times B is equals to 1, we need B is equals to 1 over 2, but 1 over 2 is not element of integers. Generally, for any integer A is not equal to positive or negative 1, the equation A times B is equals to 1 does not have solution. B is not an element of integers because the inverse of an integer A under multiplication is 1 over A, which is not an integer unless A is equals to positive or negative 1. So therefore, the set of integers with multiplication is a monoid but not a group. For example 1.3, that be a vector space, then vector with addition is an abelian group. The definition of abelian group is a set with an operation that is associative, has identity, has an inverse, and is commutative. Let's verify the vector with addition is an abelian group. In the associativity, for all u, v, w is an element of vector. Then the quantity u plus v plus w is equal to u plus the quantity of v plus w. In the identity, there exists an element 0 is an element of vector, such that for every v is an element of vector. Then b plus 0 is equals to 0 plus b is equals to b. For the inverse, for every b is an element of vector, there exists an element of negative b, such that b plus negative b is equals to negative b plus v is equals to 0. In the commutativity, for all u b is an element of vector, then u plus v is equals to v plus u. So therefore, the vector with addition is an abelian group because it satisfies the following properties. For example, 1.4, let n is an element of integers with addition. Let be the set of all n times n matrices over the real numbers. Then the set of all n times n matrices over the real numbers with addition is an abelian group. Let be the set of all n times n matrices over the complex number. Then the set of all n times n matrices over the complex number with addition is an abelian group. The set of all n times n matrices over real numbers is a set of all n times n matrices with the real entries. The set of all n times n matrices over the complex number is the set of all n times n matrices with the complex entries. Let's verify the set of all n times n matrices over the real numbers and the set of all n times n matrices over the complex number are an abelian group. In the associativity, for all A, B, C is an element of the set of all n times n matrices over real numbers, or the set of all n times n matrices over the complex number. Then the quantity A plus B plus C is equals to A plus the quantity B plus C. For the identity, there exists an identity element 0 is an element of the set of all n times n matrices over the real numbers, or the set of all n times n matrices over complex number, such that for every A is an element of set of all n times n matrices over real numbers, or the set of all n times n matrices over the complex number. Then A plus 0 is equals to 0 plus A is equals to A. For the inverse, for every A is an element of the set of all n times n matrices over real numbers, or the set of all n times n matrices over the complex number. There exists an element of negative A is an element of the set of all n times n matrices over real numbers, or the set of all n times n matrices over the complex number, such that A plus negative A is equals to negative A plus A is equals to 0. In the commutativity, for all A, B is an element of the set of all n times n matrices over real numbers, or the set of all n times n matrices over complex number, then A plus B is equals to B plus A. So therefore, the set of all n times n matrices of a real number with addition, and the set of all n times n matrices over a complex number with addition is an abelian group because it satisfies the following properties. For example, 1.5, the general linear group, that is 2 by 2 matrix for real numbers is equal to A is equal to the matrix of ABCD, where ABCD is an element of real numbers. Determinant A is equal to AD minus BC is not equal to 0. Is general linear group, that is 2 by 2 matrix for real numbers with multiplication a group? Yes, but not an abelian group. So let's verify if the general linear group, that is 2 by 2 matrix for real numbers in abelian group. First, in the associativity, matrix multiplication is associative for any ABC is an element of general linear group, that is 2 by 2 matrix for real numbers. Then A times the quantity of B times C is equals to the quantity of A times B times C. For the identity element of general linear group, that is 2 by 2 matrix for real number, is the identity matrix where identity is 1001. For any A is an element of general linear group, that is 2 by 2 matrix for real numbers. Then A times I is equals to I times A equals to A. For the inverse, every element A is an element of general linear group, that is 2 by 2 matrix. For real numbers, the inverse A is an element of general linear group, that is 2 by 2 matrix for real numbers, such that A times A inverse is equals to A inverse times A is equals to I. The inverse of 2 by 2 matrix A is equals to ABCD, with the determinant A is equal to AD minus BC is not equal to 0, is given by A inverse is equal to 1 over determinant of A matrix of D, negative B, negative C, and A. So let's check the commutativity. Matrix multiplication is not commutative. In general, for two matrices, A, B is an element of general linear group, that is 2 by 2 matrix for real numbers, then A times B is not equal to B times A. So therefore, the general linear group, that is 2 by 2 matrix for real numbers with matrix multiplication, is a group but not an abelian group.
Hi, my name is Leah Jane Ferrer and I will be discussing Theorem 1, 2, and 3 of groups. So in a Theorem 1, in a group, the identity element is unique or uniqueness of the identity element. We have proof that let G star be a group and let us assume that E and F are the two identity elements of group G. So in the first case, let E an element G be the general identity of element group G, and F an element G be the identity element of group G. So E star F is equal to F a star E equal to E. So in the second case, let F an element G be the general identity element of group G, and E element G be the identity element of group G. So F star E is equal to E star F equal to F. So from the first and second case, E is equal to F. Hence, in a group G, the identity element is unique. So we have Theorem 2, it is called cancellation law. So let B a group, then for A, B, and C is an element of group. AB equals AC is to B equals C, and that is called left cancellation law. BA equals CA is to B equals C, and that is called right cancellation law. So we have proof that let G be a group and E be the identity element in group G. We also consider A inverse, and equals to A inverse A is equal to E. So left cancellation law, consider AB is equal to AC. A inverse times AB is equal to A inverse times AC. So A inverse A times B is equal to A inverse A times C. So EB equals EC is from equation 1. B is equal to C. Thus, AB equal AC is to B equals C. Hence, the left cancellation law is proved. Right cancellation law, we consider BA equals CA. BA times A inverse equals CA times A inverse, and B times AA inverse equals C times AA inverse. BE equals CE, it is from equation 1, so B is equals to C. Thus, BA equals CA is to B equals C. Hence, the right cancellation law is proved. So we have Theorem 3. For any non-empty set A, the set S sub A of all permutations of A is a group under permutation multiplication. So the group S sub A and degree is called the symmetric group of A. If A is a finite set with n elements, S sub A may be denoted by S sub n, and the group S sub A and degree is then called the symmetric group of degree n. So we have proof. The first proof is theorem 6.1.5 is satisfied. For the second proof is corollary 6.1.10 is also satisfied. And for the third proof, corollary 7.1.5 is also satisfied. From corollary 7.1.5, the identity of S sub A is the identity permutation. A is to A, which holds every element of A is fixed. So for the fourth proof, corollary 7.2.3 is also satisfied. From corollary 7.2.3, the inverse of a permutation sigma B is equal to A. So for sigma, A is to A is the permutation sigma inverse for A is to A such that for every A is an element of A. Sigma inverse times A is equal to B if and only if sigma B is equal to A. So in particular, if A is a n set, the inverse of the cycle A sub 1, A sub 2, and so on is the cycle of A sub n minus 1, and so on. So in the direct product, the Cartesian product of the sets in group may be used to construct additional groups. This section shows how this can be done. So let G sub 1 star and G sub 2 times be any two groups and consider any two ordered pairs A, B, and C, D. In the Cartesian product, G sub 1 times G sub 2 of the sets G sub 1 and G sub 2 because by DEF, A and C are elements of G sub 1, so A star C is an element of G sub 1. Similarly, B times D will be an element of G sub 2 if we now define on G sub 1 times G sub 2 as follows. So for all A, B, and C, D is an element of G sub 1 times G sub 2, A, B times C, D is equal to A star C, B times D. So it becomes clear that is an element of G sub 1 times G sub 2, AB times CD. So this makes a binary operation on G sub 1 times G sub 2. And we have thus just proved the following.
Theorem 4. Let G sub 1 star and G sub 2 times be grouped and defined on G sub 1 times G sub 2 as follows. Quantity A and B times quantity C and Z is equal to quantity A star C and B times D. Then is a binary operation on G sub 1 times G sub 2. Definition. The binary operation on set of two groups are defined in the definition in the third side. Theorem 5. If G sub 1 star and G sub 2 times are grouped, then the G sub 1 times G sub 2 is a group under multiplication by components. Some of the example of this is G sub 1 times G sub 2 is a group. So the definition of this is if G sub 1 and G sub 2 are groups, the group of G sub 1 times G sub 2 star, where is a multiplication by components, is called the direct product of the group of G sub 1 and G sub 2, and may be referred to simply as group G sub 1 and G sub 2. So the last theorem is theorem 6, a generalization. Corollary. The given groups is G sub 1, star sub 1, G sub 2, star sub 2, G sub 3, and star sub 3, and so on until G sub n and star sub n. The operation of the Cartesian products is G sub 1 times G sub 2 times G sub 3 times and so on until G sub n. Of group of G sub 1 times G sub 2 times G sub 3 and so on until G sub n is defined as follows. Quantity A sub 1 times A sub 2 and so on until A sub n times quantity B sub 1, B sub 2, and so on until B sub n is equal to quantity A sub 1, star sub 1, B sub 1, and A sub 2, star sub 2, B sub 2, and so on until A sub n, star sub n, B sub n is a binary operation on G sub 1 times G sub 2 times G sub 3 and so on until G sub n. This operation is called multiplication of components. Theorem: if G sub 1, G sub 2, and so on until G sub n are grouped, then G sub 1 times G sub 2 times G sub 3 and so on until G sub n is a group under composition by components. This group is called the direct product of the groups G sub 1, G sub 2, G sub 3, and so on until G sub n. So the last part is the notations. The direct product of G sub 1 times G sub 2 times G sub 3 and so on until G sub n may be denoted by n. Notation sub 1 is equal to G sub 1. If the operation in every G is commutative, the additive notation of G sub 1 plus G sub 2 is D plus G sub 1 plus and so on until G sub n. Or n notation sub 1 is equal to G sub 1 may be used instead, and the direct product is called the direct of sum.
Good day, everyone. I'm Ronami Promonest, and I will be discussing the exercises. So let's proceed. So in test 1, the problem is that in each of the following, determine if the indicated G is a group under the indicated operation. If G is not a group, indicate which group axiom or axioms has or have not been satisfied. So number 1, G is equal to Z, operation is subtraction. Number 2, G is equal to R star, operation is defined by A times B equal A over B. And number 3 is that G is equal to R star times R, operation is defined by A and B times C and D is equal to AC and AD plus B. And the test 2, number 1, determine if Z is a group under F given that for all A and B is an element of Z and AFB minus AB. And number 2, prove that R minus 1 or real numbers minus 1 star is a group if star is defined by A star B is equal to A plus B minus AB for all A and B is an element of real numbers negative 1. So first, let us answer the test 1 number 1, which is G is equal to Z. Operation is subtraction. So by proving this, we should satisfy the definition of a group. So first, in closure property. So A is equal to 1 and B is equal to negative 1. So let's assume that this is the value of A and B. So A times B is equal to A minus B. And A times B is equal to 1 minus negative 1 because we substitute the value of AB. And A times B is equal to 1 plus 1. It is positive because negative plus negative equal to positive. So A times B is equal to 2. So it is a closure property. And let's proceed to associative property. Let's see if it is associative property. So A times B times C is equal to A times B times C. And A minus B times C is equal to A times B minus C. And A minus B minus C is equal to A minus B minus C. So A minus B minus C is equal to A minus B plus C.
So it is not associative property because they are not equal. Next, identity property. So A times B is equal to A, and on the other side, E times A is equal to A. And A minus E is equal to A. And E minus A is equal to A. And negative E is equal to A minus A because we transpose the A in the other side. That's why it become negative A. And E is equal to A plus A because we also transpose the negative A, so it became A positive. So negative E is equal to 0. And negative E in the other side is equal to 2A. So they are not identity property because they are also not equal. So let's proceed to the inverse property. A times A raised to negative 1 is equal to E, and A raised to negative 1 times A is equal to E. So A minus A raised to negative 1 is equal to 0, and on the other side, A raised to negative 1 minus A is equal to 2A. And negative A raised to negative 1 is equal to negative A. And on the other side, negative A raised to negative 1 is equal to 2A plus A. So A negative 1 is equal to A. And on the other side, A inverse is equal to 3A. So therefore we can conclude that the inverse has not been satisfied because they are not equal. So the number 1 is not a group because it does not satisfy the definition of a group. So let's proceed to number 2, test 1. G is equal to R star. Operation is defined by A times B is equal to A absolute value of B. So to prove this, it must satisfy the definition of a group. So first, the closure property. Let us see if it is a closure property or not. So A is equal to 2 and B is equal to 3 because they are real numbers. So A times B is equal to A absolute value of B. And A times B is equal to 2 absolute value of 3. We substitute the A and the value of A and B. So A times B is equal to 2 times 3. So A times B is equal to 6. So it is closed and it is a closure property. Next is the associative property. A times B times C is equal to A times B times C. So A absolute value of B times C is equal to A times B absolute value of C. So AB times C is equal to A times BC. So AB absolute value of C is equal to A absolute value of BC. So the answer is ABC is equal to ABC. So they are equal and it is associative property. Next, the identity property. Let us prove it is if it is a identity property. So A times E is equal to A, and A absolute value of E is equal to A, and 1 over A is equal to 1 over A times AE is equal to A times 1 over A. So 1 is equal to 1. So it is identity property. And the last one is that inverse property. So A times A raised to negative 1 is equal to R, or A times A inverse is equal to E. So A absolute value of A inverse is equal to E. And 1 over A is equal to A absolute value of A and A inverse is equal to 1 times 1 over A. So A inverse is equal to 1 over A. And it satisfies the condition in inverse. So we can conclude that the number 2 is a group because it satisfies the 4 properties. Next, let's proceed to number 3, test 1, which is G is equal to R star times R. Operation is defined by A and B times C and D is equal to AC and AD plus B. So let's prove if it is a group or not. First, let's identify if it is a closure property. So A is equal to 1 and B is equal to negative 2 and C is equal to 3 and D is equal to negative 4 because they are all real numbers. Let's just assume. So A and B times C and D is equal to AC and AD plus B, as you can see on the screen. And A and B times C and D is equal to 1 times 3 and 1 minus 1 times negative 4 plus negative 2. We substitute the value of A, B, C, and D. So A and B times C and D is equal to 3, negative 4, and 2. Minus 2. So A and B times C and D is equal to 3 and negative 6. So it is closure property because it satisfies the because it is a real number. Next, let's proceed to associative property. So A and B times C and D times EF is equal to A and B times CD times E and F. So AC and AD plus B times EF is equal to A and B times CE and CF and plus B. So AC and ACF plus AD plus B is equal to ACE and ACF plus D plus B. So the answer is ACE is equal to ACF. ACE and ACF plus AD plus B is equal to ACE, ACF plus AD plus B. So it is associative property because they are both equal to each other. Next, let's proceed to inverse property. A and B times A inverse and A inverse is equal to E and E. And A inverse and A inverse plus B is equal to 0, 0 or 1, 0. So 1 over A is equal to A inverse is equal to 1 times 1 over A. So A inverse is equal to 1 over A. And 1 A and A inverse plus B is equal to 0. So 1 over A times A inverse is equal to B times 1 over A. So the answer is A inverse is equal, so the answer of A inverse is equal to negative B over A. So let's assume that A is equal to 1 and A inverse is equal to 1 and B is equal to negative 2 and B inverse is equal to negative 2 over 1, or let's say B inverse is equal to 2. So A and B times A inverse and A inverse is equal to E, or element rather. So 1 and negative 2 times 1 and 2 is equal to 1. 1 times 1 and 1 times 2 plus negative 2. We substitute the value of E. So 1 and 2 times 1 and 2 is equal to 1 and 0. So it is an inverse property because it satisfies the condition. Next and lastly is the identity property. So A and B times E and E is equal to AB. So A and E plus B is equal to AB. So 1 over A times AE is equal to A times 1 over A. So E is equal to 1. And on the other side, AE plus B is equal to B, and AE is equal to B minus B. And AE is equal to 0. And E is equal to 0. So E is equal to 1 and E is equal to 0. So let's assume that A is equal to 1 and B is equal to negative 2 to prove this identity property. So A and B times EE is equal to AB. Let's substitute the value of A and B and DE. So 1 and negative 2 times 1 and 0 is equal to 1 and negative 2. And 1 times 1 and 1 times 0 plus negative 2 is equal to 1 negative 2. So 1 is equal to 1 and negative 2 is equal to 1 and negative 2. So it is a identity property because it satisfies also the condition. So therefore we can conclude that this number 3 is a group because it satisfies the definition of a group. So let's proceed to the test 2 number 1, which is determine if Z is a group under star given that for all A and B is an element of Z and A times B or A star B is equal to negative AB. So as we can see here in the screen that it has been satisfied all the definition of a group, which is a here in closure property it is closed because 3 is an element of Z, and in identity property it is 4 is equal to 4, you can see, and it is identity property because it satisfies the condition. And here in associative property ABC is equal to ABC, so they are both equal and they are associative because it satisfies also the condition. And here in inverse it also satisfies the condition, so we can conclude that number 1 test 2 is a group. Next, let's proceed to the number 2 of test 2, which is prove that R negative 1 star is a group and is defined by A times B, or A star B is equal to A plus B minus AB. Wherein for all AB is an element of R minus 1. So as you can see, it does not satisfy the definition of a group because um, here in closure it is closed, and in identity it has been satisfied. Also in associative property it has been satisfied the condition, but in inverse property it does not satisfy, or it is not an inverse because it does not satisfy the condition. So therefore we can conclude that this number 2 is not a group because it does not satisfy the definition of a group. So the summary of this discussion is that group theory in mathematics studies a set of elements consolidated for an operation. It includes inset theory, which combines elements to produce a third, and geometric theory, which studies finitely produced groups. The four axioms of group theory are closure, associativity, invertibility, and identity. This article explains group theory's definitions, applications, and examples.